In this video, I'm going to cover how to write a binary search tree using code. I'm going to write the binary search tree using Kotlin. If you want to learn more about what a binary search tree is or how it operates at a high level, please watch my last two videos. In this video, we are going to implement these different methods. Add, which will add new data to our tree. Contains, which will return whether or not data is in the tree. Size, which returns the size of the tree. Is empty, which returns if the tree is empty or not. Remove, which removes a piece of data from the tree. And clone, which copies the tree and returns the copy. Once I am done writing a method, I will put the method at the bottom of the file so it's out of way for the rest of the video. That way we can focus on what is left rather than having to scroll through. One of the first things we need to do is we need to create a node class. The node class needs to hold the value for that node as well as a pointer to the left node and to the right node. We're having the left node and right node be nullable so that we can know when we've reached the leaf nodes or the nodes that don't have any children. The value is where we will be putting all of our data, and that is what we're going to use for comparison. One thing to note is while we're having t be declared as comparable in the binary search tree, we aren't doing that in the node. The reason we're doing this is the binary search tree type, t, will always be used for the node type. And so the comparable attribute will always be there implicitly, so we do not have to define it. So now that we have our node class, we're going to define our root. Our root is nullable because empty binary search trees don't have a root node. We're also going to define a size variable. The size variable allows us to track the size of the binary search tree without having to calculate it. I will, later on in the video, show how to calculate the size of the binary search tree without having to keep a running total. One of the advantages of the running total is it does help in speed for getting the size calculation. It's just always instantaneous since it's always updated. Downside is it's more bug prone since you have to remember to always update the size variable anywhere you change the tree, and it also can take more memory. On most modern systems, it's not going to be too big of a concern in a typical application, but in memory constrained environment or where you have massive amounts of data, being able to save a few bytes here or there might be worth the cost of doing the calculation rather than storing it in a variable. Root and size defined, we can now define our size and isEmpty methods. Our size method is just going to return our size variable, and our isEmpty method is going to return if root is equal to null. The reason I'm returning root equals to null instead of size equals 0 is that when we switch over to doing the calculation for size rather than relying on a running variable, I still want isEmpty to run in constant time and not rely on counting all the nodes in our tree. By doing a root check for isEmpty, we guarantee that regardless of how our size is calculated, we will always run in constant time for our isEmpty check. Now that these two methods are done, I am going to move them to the bottom of the class just so they're out of the way. The next method we're going to work on is the add method. The add method will have a special case for when the tree is empty. If the tree is empty, that means we don't have a root node, and so our new value is just going to be the root. Since we are keeping a running total of the size, we also need to update the size variable. Since we've done everything we need to, we can return early. For everything else, what we need to do is we need to find a spot where we should insert the new data. We do this by having a current node that indicates where we are in the tree, and then we base all of our searching off of the current node. In this case, I'm using a while true loop since I will be handling every possible case in the loop, and I'm going to take care of breaking out of the loop. What I'm doing here is this value that we're inserting, I'm comparing against the value at the current node. This is useful since it does a less than, equals, or greater than comparison at once, and then puts the result in my comparison. If the value is less than, comparison will be less than 0. If it is equal, comparison will be equal to 0. And if it's greater than, comparison will be greater than 0. By doing a single comparison, I can guarantee that even if the data takes a long time to compare, such as it's megabytes of text, when I do all those different comparisons for those 3 different buckets, those checks are all very, very quick since I'm only doing the expensive check once. What we're now going to do is do the left navigation case. Again, comparison being less than 0 indicates that our value is less than the current node value. If our current node going left exists, then we will update our current node point to the left child. It moves us left in the tree. Otherwise, we don't have any nodes to move to, and so our new node should get inserted instead. Again, since we're doing a running total for the size, we also have to update that. Finally, we can return from the method. This return statement also ends the while loop. Next, what we're going to do is if the comparison is greater than 0, we're going to move to the right. This code is very similar to this code up here. The only difference being instead of doing .left, we're doing .right. The final case is to handle if we found a node already in the tree. In that case, what I'm going to do for this tree is to ignore inserting the new node since it's already there. By ignoring the insertion if the value is already there, what we are doing is creating a set where if you add 3 5 times, it's only in the tree once. That means when you remove 3, you remove it entirely. If you want to keep the 5 copies of 3, all you need to do is remove this else statement and remove this if statement here. And now what will happen is when you are less than, you will go through this branch. Otherwise, if you are greater than or equal to, you will move through this branch. This little change will work for the rest of the code. If you are writing a tree that allows you to have duplicate values, you can even simplify this value compared to with a value less than current node.value. With this, you no longer have to do the 3-way comparison. I will have both versions of the add method in the code online. The one that allows duplicate versions will be commented out, but you can uncomment it to switch between the two. With this, our add method is finished. The next method we're doing is the contains method. This is going to return a true or false value depending on whether or not the passed-in value is present in the tree. I'm going to also have a current node. I'm going to start it off being set to the root node. One of the things you'll notice is that in contains, I don't have the double exclamation points at the end, whereas in add, I do. In our add method, the double exclamation points means that this value cannot be null. We've already done the check and handled the case where root is null. However, in our contains, we aren't doing a separate check to see if our root is empty. Instead, we are going to handle that check as part of the while loop condition. If our root is null, we'll get down here, we won't go through the while loop, and we'll come to the end of it. In that case, we'll return false. This also means that at any point, if we get a null node, we will just automatically exit the loop and return false. This is a really nice trick to help avoid both an infinite while loop while also lowering the amount of return statements we need to have inside of the loop. I am going to do a 3-way comparison here, since we do have 3 buckets that we are going to be handling: less than, equals, and greater than. And each one of those is going to need slightly different logic. We'll start with the less than. So if our value is less than the current value, we're going to move to the left. And we'll do the opposite for greater than. Finally, we have the case where the values match. In this case, we want to return true since it means we found the value we're looking for. And with this, our contains method is done. Previously, I had written some unit tests to test a lot of these methods, such as isEmpty, size, contains, and add. I'll run some of those tests. A few of them won't work at this stage, but some of them will. As you can see, there are a few tests that are passing. Our add test right here is passing, which means we are properly adding and searching for values in our tree. As we finish the last few methods, the rest of our tests will start to pass. Since contains is done, I'm going to put this at the bottom of the file. Next on the list is the remove method. Remove method is the most complicated method of the entire binary search tree. With remove, we do have to do a search for the node we're looking for, similar to contains. However, unlike contains, we also have to keep track of the parent node since we will be changing the parent in most cases. We start the parent node to null because when we initially go through, we don't have a parent node for the root. We need to indicate that there is no parent node, and we'll be handling those cases a little bit differently throughout the code. Next, we'll have the current node, which is the root. We are going to be doing the null checks on the current node, so we don't have to do the double exclamation points at the end. Instead, we'll just do a while occur not equal to null. Now that we have this, we're going to do our three-way comparison again. The three-way comparison will allow us to do the three buckets of less than, greater than, equals to very efficiently. If our three-way comparison shows that our target value is less than the current value, we will go to the left. When we move, we need to make sure we update the parent node to point to the current node before we move. That way, after we move, we know what the parent node was, as well as what the current node is. The greater than case is very similar, just using .right instead of .left. Finally, the equals case is the most challenging of these cases since we have to choose between the removal strategy. We have the leaf removal, the redirect removal, the successor removal, and the successor redirect removal. We are going to be choosing between. Since choosing the category of strategy is based off of the number of children, we will be counting the number of children at our current node. Next, we need to do the actual strategy selection based on the number of children. None of these methods exist yet, so we're going to create them, but we will be creating all three of these methods as private methods. That way, outside code isn't calling it and getting our tree into a bad state. The leaf strategy is to simply delete the current node. However, we need to know about the parent so that we delete the correct node. We're going to handle the case of if the parent is null, or if the parent left child is the current node, or if the parent's right child is the current node. We will first start off with if the parent is null. If the parent is null, that means that the current leaf node is the root node. If we're deleting the root node, that means we're empty, so our size has to be 0. Otherwise, we're going to remove the correct child node. Now, instead of updating size in all of these little if statements, we're going to move the size update out of here and up into our loop. We're also going to return here, make sure we break out of our while loop. We need to define our remove redirect and remove successor methods. For the remove redirect node, we will be pointing the parent node to the removed node's children. To do this, we'll have a next node, which will be the next node for the parent node to point to. In Kotlin, we don't have a ternary operator. Instead, we use if statements. And then the last statement in the if statement is the result value of the if statement. In this case, if node removal left is not equal to null, we'll get the left node, otherwise we'll get the right node. Next, we need a handle setting the correct parent value. If our parent is null, that means this is the root node, and so we'll just redirect our root pointer to the next node. In other cases, what we need to do is change the correct parent pointer, whether it's the parent.left or parent.right. With this, we have finished our remove redirect. Now there's only the remove successor function left. The remove successor method is a bit more complicated since we're also going to be selecting between the two strategies of remove successor, redirect. Remove successor redirect, we need to have the parent node point to the new child node. There is a little trick we can do to make things a little bit simpler. Instead of removing the node completely, we're just going to swap the value, and then we'll just have to worry about updating the successor's parent node. So first, we're going to keep track of the parent for our successor node. Our successor parent is going to start off as the removal node, since we're going to be moving right as the first step of our search, and then 0 or more times move left. Now that we've gone to the right ones, we need to go left as far as we can. Again, we need to make sure that the parent gets updated so we have the correct parent by the time we're done with the loop. Now that we've done this, we have our successor node as well as its parent node. And instead of trying to update the parent node of our removed node, we're just going to swap the values of the removed node with the successor node. This is going to be how we replace the removed node with the successor node. Now that we have our successor node, we need to remove it from the tree while also making sure that its parent points to any children we have. There's going to be two cases for the parent node. The first is if the parent node is our removal node. In that case, we're updating our parent's right child instead of the left child. So we're going to have two cases for the parent node. The first is if parent node is not the node we removed. In that case, we're going to update the left child. In the other case, the successor node is the node we're removing, in which case, since we did a step to the right, we need to update the right child. So now that we are selecting which child we need to update, we now have to do that update. Since our successor can only have a child to the right, we only need to check that node. If there are no children, we can just remove the successor's left child. One of the things you may have noticed is that if our successor right is null, then setting it to successor right would still give us the same result. Instead of doing this check to see if we need to redirect the parent, we can always redirect the parent to whatever our successor's right child is, and it will give us the correct answer. Now that we have it simplified, we can do the same thing for the right, just change .left to .right. And with this, we have finished remove successor. If we run the test, we should notice that almost all the tests are passing. The only test not passing is for cloning or copying the whole tree. For that, I am going to put the code we just wrote down the bottom, and then we're going to focus on the clone method. With the clone method, we're going to create a full deep copy of the entire tree. That way, if you ever want to modify a copy without changing the original, you'll be able to. For this, we first need to have a new tree. Next, we're going to create a queue to have all the nodes. I'm having the queue be holding nullable values since the code is a little bit simpler if I just do the null check inside the while loop instead of doing null checks throughout the code. Now that we have our queue, we need to add our root to the queue. Our root might be null, but that's okay since we're going to handle the null check inside the loop. While our queue is not empty, we're going to pull items out of the queue and we're going to process them. If the item we pulled off the queue is not null, we're going to add it to our copy. We're now going to take our left and right nodes and just add them to the queue. Since the null check is handled inside the loop, we don't have to check if they're null right now. They'll just be checked automatically once they're pulled off the queue. Finally, we return our new tree. We run the code, all the tests should pass. And did they do? Again, we're going to add this to the very end. And now we're going to look at how to calculate the size without having a running count. The way we do this is going to be very similar to the clone, where we have a queue that we use to process the item, and then we count all the non-null items on that queue. Unlike last time where we added the element to the new tree, we're just going to increment our count. With this now, we have a functional size, and we can compile it and we'll see that all the tests pass. Again, this method is also going to be in the code online, but it's just going to be commented out. If you want to switch between the size with the running total and the size with the calculation, all you have to do is uncomment the method. Thanks for watching. Remember to like and subscribe.